Okay, so let's trying to go through the last one's problem first. Uh, so the first problem is like a multiplication in a different number base, and so this is in the base 8. In the base 8, basically multiplying 1000 is still equivalent to in the 10 base. 10 base, basically you're just adding 3 0. So in the 8 base, actually in any base, if you multiply like a all zero, a all zero factor. All zero means that the leading is 1 and remaining is all 0. Then basically it is so this in the base 8 is actually equivalent to 8 to the third power. So basically when you multiply this number to the 8 to the third power, then basically you just adding the power to each digit, because this number actually could be written away as like equal to 4 multiply 8 square plus 3 multiply 8 first plus 6 multiply 8 to the 0. So if you multiply a 1000, basically is 1 multiply 8 to the third power, then use the distributive property. So this is how it works, 1, 2, 3. And it's actually could be written as in the expanded form, it's 4 multiply 8 to the fifth plus 3 multiply 8 to the fourth and plus 6 multiply 8 to the third. So given this format, if we write this expanded form back into the 8-based integer, it's going to be exactly like 4. And this, because this is followed by 5 0. So basically it's 1, 2, 3, 4, 5, 0. That's base 8. And here is basically plus and 3, 0, 0, 0, 0, base 8 plus 6, 0, 0, 0, and the base 8. Then basically you can combine back into 4, 3, 6, and 0, 0, 0, base 8. So basically, you can prove this in any number base. So basically, it's just a matter of appending 0 if you dealing with a different number base system. Then let's try to do this problem. And so this problem basically is dealing with the factors of so this number is already prime factorized. So all the possible factors, if you add them up, will be equal to 1 plus 2 and 1 plus 3 and 1 plus 5 and 1 plus 7 and then 1 plus 11. So, just looking at the number of the factor you can have in here, let's review. This is actually a topic we just taught last time. Based on the number of the factor for this prime, for prime 2, we can pick 2 to the 0 or 2 to the first. So basically, we can pick either 1 or 2. And then for 3, we can pick 1 or 3. Because the whole product is the original number. Any possible factor of this original number is a pick, a strategic pick of those between those 5 factors. If you pick none, then it's just 1. If you pick all, it's original number. If you pick part of it, it's going to be one of the factors. And so, there are 2 ways to pick 2, 2 ways to pick 3. So there are 2 to the 5th way to pick each factor. And what are those factors? Those factors, for example, if you just pick 1, it's going to be 1, 1, 1, 1, 1. So basically, the product, the uncombined product of this actually have 32 terms. So will be equal to the cardinality matches. So the reason behind this, why all the sum of the factor is equal to this, is fairly easy. It's just adding it. So basically, if I change 2 multiply 3 into like 2 square multiply 3 multiply 5 all the way, then basically in the first term, it's going to be 1 plus 2 plus 4. Everything will stay the same. So basically, this is, so let's do a summary. Number of the factor, for example, this is a much bigger number. It has much higher power. So the number of the factor basically is, so in the number theory, first we have to remember a theorem. The theorem is called arithmetic, the fundamental theorem of arithmetics. A fundamental theorem of arithmetic is actually quite famous. It was proven by Gauss. So that's famous guy that, so that theorem states that any integer, positive integer, could be factored into like prime 1 multiply prime 2 multiply all the way to prime n. And for each, for example, this is prime I, and maybe let me just ignore in the middle. So basically, and for this one, and then its power is let's I1. So its index for each prime factor, index 2 and index n. So basically, all the integer could be factored into this format. And then the number of the factor is actually equal to I1 plus 1 and I2 plus 1 all the way to multiply to like IN plus 1. So basically, based on this, and also the sum, so this is the number of the factors. Then sum of the factor, sum of the factors actually is equal to like, for the first prime, we have to like p to the 0 plus p to the 1 and plus all the way to p to the I1 and multiply p2 to the 0 plus p2 to the first plus all the way to pi2. Then you have to multiply all those. So basically, you have to try to calculate the sum of the factor of this number. It's going to be huge. You will actually have to like 1 plus 2 plus all the way to like 2 to the 11th in the first factor. Then the second factor, it will be 1 plus 3 plus. So basically, happily it didn't try to ask you the sum of the factor for the second big number, but it's just ask for the number of the factors. So, but the first one, it's asking for the sum of the factors, so you're just adding it this way. But anyway, sum of the factor for the first one is actually still relatively easy. We can say that, 1 plus 2 is just 3, multiply 4, multiply 6, multiply 8, multiply 12. Then for the number of the factor found on the bottom, it's actually 11 plus 1 is 12, and 7 plus 1 is 8. 5 plus 1 is 6, 3 plus 1 equal to 4, and 2 plus 1 equal to 3. So you find out they are all be able to cancel out. So actually the solution of this problem is just 1. And let's trying to see this number. So this problem is that this problem, I will say, how do you take on this type of problem? The way to take on this type of problem is first do pattern observation by listing a table. So basically you can listing a table of data first, for example, saying that, 0 factorial is just equal to 1, 1 factorial equals to, you observe some, because first you possibly will be 1, 2, then 3 will be 6, 4 will be 24, then 5 will be 120. So only reaching 5, you get a 0. And then you realize that, how to contribute a 0 in the n factorial's end is that you actually have to introduce a factor of 5. So basically, because anything end with 0, it's basically 2 multiply 5, means that you have a factor of that number of 2 multiply 5. They are abundant of 2 because starting from 2 factorials, there are a lot of two factors. The scarce resource is the factor of 5. And factor of 5 is only available when you hit 5 or 5 multiple. For example, even you hit 9 factorial, it's still going to get 1, 0 because all the middle factor wouldn't add as another 5. So basically, so after listing this, I will make a second list. The second list will be like 5, I have 1, 0. So this is the n, this is the number of the 0. 5 will be 1, 0, 10 will be 2, 0, and 15 will be 3, 0, and 20 going to be 4, 0, and 25 it's actually going to be 6, 0 because for the first, for those 4, they contribute each 0, and for factor of 25 because it's 5 square, so it's going to be contribute to 0. So basically, I began to see the pattern that, if I reach 50, I'm going to have 12 because 12, 0. So basically, I can do this problem in 2 different way, and then because it looks like a 5 to any power right now is 5 square. 5 cube could be also changed again a little bit. So basically after hitting 125, so basically for below, for 25 it will contribute 6. And for 100, if you reach 100, it's going to be scaled up by 4, going to be 24. But when I get to 125, I'm going to scale up even more. So basically, it's going to be 6 multiply 5, and that's going to be 30. That's not enough, and need to plus 1, so 31. So basically, that's the way that's the type of the thinking you are doing when doing this type of the problem. So, and then this is looking building up way, but if I pick a random number, how do I calculate it? So basically, if I pick just like, for example, if I pick 100, then I actually can divide by 5. I got 20. So basically, I got 20. I got 20 factor of the 5 by just counting numbers in 5 interval. Then basically I will get, then it's actually more than 20. It's actually 24 because I build up this way. So where does the 4 missing? It's actually, I need to 100 divided by 25. I got 4 extra. So that will make up the 4. So basically, by doing build-up ways and also tear it down, and both method match. So basically that gives me a confidence of, building up the count and dissect the count in two different ways. So that's the method of researching match. I hope you learn instead of just, being able to solve this problem. So basically, what we can do is that first we kind of trying to do some guess about where it's going to land, then going to do the fine tune adjustment because um, so basically if we guess like 500, because 500 divided by 5 will give 100, 0 already, but it's going to be extra. So 500 divided by 25, you actually will end up with 20 extra 0. And so basically 120, so looks like too much. And how much more it's actually is, and I haven't divided 125 yet, 120. So if I use 500, I'm going to end up 124. So I actually get about, 1/5 more, 1/5 more 0 than 100. So basically I'm trying to use a simple scaling. If I have 1/5 more, so I'm going to scale down to about, like 400. It's going to be fairly close. So 400 is my guess, next guess. So 400 divided by 5, I'm going to get 80. So it's going to contribute 80, 85, 80 or 5 factor of 5 by every 5 interval. Then for then 400 need to divide by 25. Then I will catch the every 25 will have an extra 5. So that's going to be 25 and 150 going to be 6. So I got 16. So I get extremely close. Then 400 need to be also divided by 125. So I'm going to capture those extra factor from 5 cube and interval. And so that's going to be 3. And that's going to be 375. So basically, I'm going to get like 180 plus 16 plus 3 is actually 99. So basically 400 factorial, you actually have 99 0. So in order to have extra 0, all I need to go to is go to 405. 405 will get, but the problem was asking me the largest number, greatest possible value of n with exact 100 0. So I can push envelope a little bit more. 406 factorial, this do not contribute a single 5, then I can go up to 407, 5, or 7, 8, 9. I cannot go to 410, that it will contribute like, one more 0. So basically 409 is our answer. So this type of the problem, you just have to do some exploring. And for this problem, GCF is 6, LCM is 72. Find the sum of A and B if A greater than B and greater than 6. This type of problem, we have just have to use the Venn diagrams and complete factor all those out. So basically, 6, if we factor out the 6, is 2 multiply 3. And if we factor out 72, is actually equal to 8 multiply 9 equal to 2 to the third multiply 3 square. So we know that GCF and LCN with two numbers, it's actually a Venn diagram problem. This Venn diagram, you have to draw this and this. So the common factor is 2 and 3, 2 multiply 3. And then basically for the missing power, so for 2, I'm missing index of 2. I have a 2 square need to be put. And this 2 square is the private factor, solely belong to one side. It cannot be belong to both sides. If belong to both sides, it will combine into the middle intersection. So this side has 2 hosts, 2 square. And compare 3 of the GCF and LCM. I'm missing index 1. So for the private factor 3 to the first, I need to be putting to the other side. So basically that will have, A and B. So we can reconstruct A. So A going to be this side and B going to be this side. So this is going to be 4 multiply 6. The middle is 6 and 3 multiply 6. So 4 multiply 6 equal 24 and 3 multiply 6 equal to 18. So basically, and the A, if A equals 24, it actually satisfies this, inequality. So basically, we are able to satisfy all the needs of the original statement. And given this information, we are asking find the sum. We need to just add up A and B. And we adding them up, 24 plus 18 equals to 42. So 42 is our answer. And this problem is that a problem that you have to judge the last digit of the number, because yeah, the number is quite complex, but you know that 9 square, if you square the last digit has to be 1, and 5 square, the last digit have to be 5. And the last digit only are determined, the sum of the largest digit are only determined by the sum of themselves, and it didn't involve higher digit. So 1 plus 5 equal to 6. And we find that this number has the 6 ending, and that's the only possibility. So this one is that if you have last calendar year exactly 3 factors, and so you have to see, what type of the number has exactly 3 factor. The number, we know the number of the factor of any integer is determined by, let's review the fundamental theorem of arithmetic. It's going to be repeated again and again. So prime 1, I1, and multiply prime 2, I2, and multiply all the way prime and IN. So if has 3 factor, then it can only, this number is made up of a single prime because it cannot have other prime, because 3 itself, 3 as the number of the factor is just 3. So basically, so the number of the factor here is 3. And 3, how do we get 3? So I need to be equal to 2 to get 3, because 2 plus 1 equal to 3. So basically, it's the format of this number is going to be like P a prime number square. So we are looking for a complete square, and let's see whether or not this satisfies this definition. So let's see if this is a complete square of any number, 1849. And 1849, let's see that like 40 square is extremely close to it, 1600. And last digit is 3, or last digit is 9. So 9 can only be square of 3. So basically, if I make 43, it's going to be fairly close to it. Let's see if it's that right. 43 multiply 43. And actually it works out. So basically, you know, this number is equal to 43 square. So the next calendar will exactly 3 factor after we, consider the fundamental theorem of arithmetic. Also double check with this. We know that the next calendar year exact 3 factor has to be one of the prime factor, or one of the prime numbers complete square. And the next prime, so that's about next prime. Next prime is 47. And 47 square, let's just calculate 47. So it's 2209. So that's going to be the year. The next calendar year is 2209. So that's the number. Let's go to the next one. And so this one, basically Melody makes a list of all the proper fraction n over 496, which have the number of 1 when written in simplest term. What is some of all the positive fractions on Melody's list? So this basically, this type of number is that we have to sum up all the factors, all the possible positive fractions. And the fraction basically has if it's simplified, it's going to be 1 means that it's a complete factor. It's a proper factor, proper fraction. So it's not including 1. It do not include 496 and 496. So basically this was not included. So basically we were trying to find all the factors of the 496. 496, if we do the, we know it's divisible by 4 because 96 is divisible by 4. And so we kind of will be able to divide that. And 124. So 124, you still can be divisible by 4 because 24 is divisible by 4. So that can be, so 31. So basically it's 2 to the 4th multiply 31. So basically this is the factorization of 496. And so basically, what is sum of all the positive fractions? So basically, sum of all the positive proper fraction is that, you know, if I include 496, that's easier to do. So basically we are taking consideration of the sum of all factor, then the minus the itself, I will get all the proper fraction. So, and for this factor, we need to do the 1 plus 2 plus 4 plus 8 plus 16. So that's the number. And for this one, we actually need to put together 1 plus 31. This is the way you calculate the factors, sum of the factors. And sum of the factors, this one is 32, and this you add it together, it's 31. So basically it is 31 multiplied 32 is actually equal to 2 multiplied 16 multiplied 32. And 16 multiplied 32 is itself, basically. So basically this number, 496, is a perfect number. It's a perfect because it's a perfect number, so that actually makes this problem easy. Some of the so basically, you know, because all the proper fraction, basically, you know, if you make all the proper fraction, basically it's just a matter of picking the factors. 496, for example, the first one could be just 1, because you know, for factor of 2 I pick 0, and for index of 2, index of 31 I pick 0, then it's going to be 1. If I index of 2 I pick 1, I can pick 2. So basically it's just a matter of pick those. And after doing, so it's just this excluding the last one. Excluding the last one, basically it's going to be, you know, just if you add them all up, it is just matter 1 plus 2 plus 4 plus all the way to 16 and multiply 1 plus 31, then minus, because I don't want the biggest one, 16 multiply 31 over 496. And this we know basically is 2. And this basically is 1. So basically 2 minus 1 equal to 1. So that's the way you get this problem. And this one is that this one is actually, you know, a trick problem, and but we kind of will trying to do it in 2 different ways. And if you know, so basically you are what you are looking for is that 6 times greater than if the number is placed ahead of it. So basically, you know, it's a 6-digit number that, you know, let me label it 1, 2, 3, 4, 5, 6. Yeah, it's a 6-digit number with, you know, separation in the middle that formed by 2 3-digits side by side. If the larger of the two is placed ahead of, so the larger of the two place, the number formed is 6 times greater than this. So if they X, Y, Z, A, B, C, so assume this is the larger one, and then the other one, the smaller one, is A, B, C, X, Y, Z, and they have a 6-time difference. And 6-time difference basically is just number rotation in the 7 factors, in the 7 fractions. We know that 1/7 basically is equal to, you know, 1/7 is actually 0.14285 7. So basically, and so this is actually just a trick problem. So this is 285714, and then if you know the trick, if you know the trick, basically 6/7 is actually equal to, this is 0 point, and 857,142. So basically 87142, because when you multiply this by 6 times, it actually will rotate into this one. So basically, the digit works behind the decimal also will work in front of decimal by shifting decimal by 6 position. So basically, this is just some trick problems. So if you find, like, if there's a 3-digit shift, multiple relationship, you might want to dig into this one. It actually can work for like 6 times, 2 times, and something like number shifting. So it's all like number shifting. So this one basically is shifting up those number by 2 positions and rotate 14 to the end. So this is one of those. But you can also solve this problem just by doing the, like, algebra. So basically, doing the algebra is just a little bit more challenging. And so let's see, if you want to do the algebra, basically, the larger number 1000x plus y. Why 1000x plus y? Because the larger 3-digit x, is actually 1000 times of its face value by placing at 3-digit higher. And this has 6-time relationship. You just do it algebraically. When you do it algebraically, then what you will get is actually, this is multiple of x. You combine it, going to have 994x. And here is the, y term. And when you combine it, it's going to be 5,999. Then when you simplify it, you can simplify it to this format. And given this format, these two numbers are coprime. The obvious way, any number could satisfy this, 3-digit number could satisfy this relationship, has to be like x equals 557 and y equal to 142. And that's the only selection. So that's the only selection, then you actually is able to add them up. After you adding it up, it's going to be 999. So that is the way that you can solve this type of problem. And but then if you remember this trick, basically, because 1/6 basically is 6 times of 1/7. By multiply 6 times of the infinite rotating decimals, it actually will achieve this. And then if you just, it works for infinite cycles, it also works for one cycle. So basically, so if it worked for one cycle, so we actually can guess this number directly. And then we actually can just add the digit. We also get 999. And so this problem is that the 356 graders, so it's a big circle. Let me see, my company has something. Okay, glad it's not my problem. And so 356 graders standing a big circle, they count off to form a group. Starting at Katie, let's say Katie is here. And work to the left. So if they are facing the center, working left means that actually will work to the right, something like this way. And they count off 1 to 8, then repeat until everyone has a number. And students who share the same number to form a group. Yeah, so basically, Katie count 1, the next person will count 2, the next will count 3, it will count 4. So basically, you have 350 person. After you making a circle, basically everyone will have a count. And the count will be from 1 to 8. And you can be any one of those number. And anyone with the same number will be in the same group. So basically what we are trying to see is the remainder of the, so remainder of that number to 8. And so if Mara want to be in the same group as Katie, what is the fewest number? You know, Katie basically is remainder 1 by mod 8 because we counting by 8. So 1 is, you know, so we will trying to see if 350. So if Katie is 1, the people sitting right to the left of him is actually, you know, is 350. So let's see 350, what is the mod number of that to 8? So 8. So basically, the people labeled with 300 actually, you know, 350 is congruent to 6 mod 8. So 350 is one person to the other direction. And then I need to count from 6 all the way to down to 1. So count from, so count 1 position is 6. And then count down from 6 to 1 is equivalent to count up from 1 to 6. So basically, you know, I actually have to count 6 position. What is the field place to the right? You know, she has to stand is 6. This is the way that, you know, counting up and down. 6th place. Yeah, so basically it's about counting the mod. And so this problem is actually, you have to do some observation, and let's see. This problem, the tricky part is that the tire on the antique car have wheels with 5 spokes, but the tire are slightly different size. The larger tire in the back, so larger tire in the back is 30 inches, and while the smaller tire in the front is 27 inches. Those are different. A photographer want the photo of the car while the wheel are in the position identical to the one above. And so the wheel in the position actually have the tip of the penta star pointing down. So the star is pointing down on both front and the back wheel. And how many times will this occur in the course of quarter-mile parade if we'll begin the parade in the position shown? So basically, we know that if we go by 27 and 30 LCM, then basically we'll completely return both wheels position to the original place. So LCM of those two number works, but we have to find extra position works. They are extra position because because of the symmetry, we only need the point, the tip of the panda star pointing down, and it doesn't has to be the original star tipping point, because I can label those tipping point to be 1 to 5. I also want A, B, C, D, E. So I have like a lot of different position can work. So I have to find out all those positions. So basically here we go. First, we need to find about the way to deal with this type of the problem. The best is I first find the complete cycle. Complete cycle means everything return to its own position. So here is 1, 2, for example, 1, 2, 3, 4, and 5. And here is A, B, C, D, and E. And complete return to position means that it's the wheel on this side. A is returned to pointing down, and this is 1 is also returned to pointing down. So the cycle length of both returning to the original position. Then we also have to find if there any other position, for example, like B is pointing down related to 4 is pointing down, maybe, it still looks the same to me. And so basically we had to find out all those. So the first part is quite easy to find out, very easy, because the LCM of 27 and 30, basically this is 3 cube multiply 2 multiply 3 multiply 5. So their LCM is basically 2 multiply 3 cube multiply 5. And this basically is 10. And 27 multiplied 10 equals 270. So 270 is their LCM. 270 is 10 times the 70, and also it's 9 times 30. So basically, if the diameter is 30 inch. So if I roll 270 pi, basically, so one complete circle of the front wheel is 27, because this is diameter pi, so pi d. So by 27 multiply pi. And the complete circle of the back wheel is 30 pi. So basically, the common cycle is 270 pi. So with 270, each 270 pi distance, basically the front wheel will travel 10 complete circle and the back wheel travel 9 complete circles. They all will both return to the original position. Then, so basically that's the big cycle. Then we will try to see within the big cycle how many ways that both will pointing tip down. And pointing tip down, basically, let's try to see that, for the smaller front wheel, small front wheel, basically, there are 5 positions. And so a complete cycle obviously works, but the extra 5 positions is 27 pi divided by 5. So that's going to be 1/5 of the complete cycle is going to be 5.4 pi. So 5.4 pi is going to be tipping down again, 10.8 pi, and then it's going to be, 16.2 pi, and then that's going to be 21.6 pi, and then, so basically through a row, during those positions, it's going to be pointing down. That's for the front wheel. And for the back wheel, basically it's going to be pointing down at 5 pi and 10 pi, 15 pi, 20. I think I'm getting it wrong. It's not 5 pi. It's 6 pi and 12 pi and 18 pi and 24 pi. So basically, looks to me that there's no way that these middle one will intersect with it because these are fractions, these are integer. Then this is 30 pi. Then basically, then it will reach like 27 pi. And so I only observe the complete cycle for the front wheel, but I'm going to observe the 5 position of the integer position of the back wheel. So basically, and it's going to be six multiple. So I can trying to find the LCM of the 27 and the 6. If that works, then basically I can find both tipping down. And then for the front wheel, it's always going to be a complete cycle. But for the back wheel, it doesn't has to be complete cycle. It could be portion of the, complete cycle. So this basically is 3 cube and multiply to 3. And so basically LCM is like 54. So 54 pi. So basically for the front wheel, every complete cycle, every complete 2 cycle, the back wheel will have a position, not necessarily complete cycle, but one of the tip position will pointing to 54. For example, 6 multiply 9 is 54. So for the back wheel, basically it didn't complete 2 complete cycle. It's like still like, um, it's still 1/5 cycle away from the complete cycle. It's already has a coincide location look like this. So basically, it's just 54 pi. For 54 pi, we will achieve this. And the complete absolute cycle is 270 pi. So basically, given this information, we know that within a complete cycle, ladder to ladder, complete cycle, rotate back to A1, they're going to be 5 subcycle. Both tip will pointing down. So basically, that's the analysis you have to make to understand the data structure. So after we making this observation, then it's actually easy. We actually don't have to put on the emphasis on the big one. We only need to, because it's not asking the complete cycle. It's just asking when it will happen. It's actually the small cycle really matters. And so a quarter mile, how many inches is in the quarter mile? Is that a mile? A mile basically has 1760 feet. A quarter mile is just one. This is yard actually, and so 1760 yard multiply 3. This is feet. Then multiply 12. That's inch. So that's a complete mile. Then basically it's 1/4. So basically you have to divide by 4. Then also have to divide by 54 pi. So that's how many inch distances we have to travel for one of this appearance to happen. So basically we kind of just do the, so this going to be 350. This is 2 multiply 3 multiply 3 multiply 3. So we can cancel those. And then we will keep canceling. So anyway, let me not wasting time on calculation. So basically, it's just, if you do it, it's going to be like 94 times about. So yeah. So anyway, that's about. I think we spent about 1 hour on explaining the old problem. I think we definitely don't have enough time to go through this. I think we'll just go through some later ones, not necessarily every one of those. So the front ones, I believe those are relatively easy. The one is easy, and 2 is also easy, and um, 3 basically it's also easy. I think we'll just emphasize on using the cancellation, so you don't really have to multiply it out 10, 9, 8, 7, 6, 5, 4, 3, and 2 and 1. Then you will divide by the number of the second, and this is the second. So number of the second in a minute, number of the minute in 1 hour, and number of the hour in 1 day. So if you use the cancellation, then it's much easy to multiply it out and then do it. So basically, this is what I did. That if I do the cancellation, it's actually around like 40. Then you count up around 42, something like that. Then you count up the days, you actually got February 12th. So that's the way that you can do this. Then this problem actually is a blocker. So a lot of people that find it quite difficult, actually wasting a lot of time. It also take me several different methods. I'm going to talk about the most beautiful method. You have to think in a different way. So how many ways can a student schedule a 3 mathematics course, algebra, geometry, and number theory in a 3-period day if no two mathematical courses can be taken in consecutive period. So basically what we are, if you begin to label like one is algebra, one is geometry, one is the number series, and also the other courses, it's actually, they are, then you have 1, 2, 3, 4, 5, 6. Basically, if you consider ordering it in this way, basically there are like, you can pick 1, 3, 5, and 1, 3, 6, and 1, 4, 6, and 2, 4, 6. So basically, you actually have 4 positions to pick to just arrange those 3 classes. So you have 4 multiply then 3 factorial. So that's the way that you actually get E. But so this is a most like 99 of the people actually think about this way. Actually, I was thinking in a different way. If you think a different way, it's actually much more beautiful. You don't have to enumerate this. And a different method actually could work in a much more generic format. So let me show you the way to work in a much more generic format. A much more generic format is that, you know, uh, how many spot can be created by the separator. So consider non-math problem as separator. So we have total of like 6 period. So 6 period and so 3 mass, then 3 non-mass, are separators. So the 3 non-mass period are separators. So how do we, and we are not labeling 1, 2, 3, 4. We kind of just label the relative position. Use we are not labeling class from 1 to 6 as 6 period. We are just labeling relative position to those 3 separator. So for example, separator 1, 2, and 3. And with those 3 separator class, we created 4 position. So 1, 2, 3, 4. And those 4 position are available to choose for those 3 math class. So basically, we actually had is 4 choose 3. 4 choose 3, then multiply 3 factorial. That's going to be 24. And I actually, because when I was reading the answer of this problem, it really looks ugly. I really hate this. Then I actually I was thinking about if I change the condition a little bit, I can guarantee you cannot do it this way. This will become outruled. For example, if I say that, how many students schedule a 3 math class in a like 12 period day, if no math course can be taken consecutive period, then this method will be totally out because, how many ways for you to lay this. That's unimaginable. So with the second method, it still works because if I have a 12 period, if I 12 period three mass, then I have 9 non-mass. And 9 non-mass basically, you know, create 9 separator. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And those 9 separator and will force, to create 10 positions for you to put in the mass period. So basically it became 10 true 3 ways to pick the mass position. And see, the trick of this is actually, I just defined the separator and the position. It didn't really define the mass order. It didn't define the mass like class order, because I didn't say this has to be the first period, this have to second period. I didn't say anything. Basically, if I don't put mass in front of the first separator, this separator class going to be the first period. Otherwise, if I put a mass class in front of it, it's going to be the second. So basically, it retains the topology of the separation, because I want to separate the mass altogether, and no mass can be consecutive. With this structure, it actually keep the separation of the mass class with the flexibility of, squeezing all the right possible ways into right place. It fall into place naturally, no matter how you do it. So basically, I think this is the correct way, and this is not the correct way. And this can be used to handle smaller number of the data, but like 99% of the people is using this way if you do it right. And a lot of people don't do it right. So basically, a lot of people just simply miss this problem. So this problem in that particular year create a huge complaint. But even the answer most of people gave is actually not really desirable. So I just want to point this out. Hopefully you will understand the quintessential, the actually in a lot of the like statistic and counting problem, take the right method, take the right thinking, and make it be able to generalize. That's actually more important than just solve the problem itself. In this case, absolutely it is, because with the wrong data structure, it's unextensible. Okay, so let's try to deal with this. Let me see how do I did this problem. I actually did all those problem. Yeah, so this problem actually, I think the easiest way is to use the like number line. So if you use the number line, let me just, because I don't have too much time, I will just show what I have done. So basically, this problem, if you really mapping everything word by word, Alice say we are at least 6 miles away. So if this is the distance to the nearest town, and the range of the data Alice was claiming is 6 and more, which including the 6. And then Bob is 5 or less, including 5. And Charlie, and actually is 4 and less. So Charlie is subset of Bob. So the only thing leaving open is 5 and 6, and not including those. So basically, if no one is right, so it has to be in D. And So this problem, I actually treat this problem as a like a racial proportion problem, because this website is having review, and the review will give a score of 1 for a like and will decrease 1 for dislike. So basically, assume you can only make, like or dislike. You don't have, no action at button. So basically, if you vote, you have to take one of the stance. So if you have 65% voted like, then the remaining 35% don't like it. So we have to take consideration of that. The combined effect of 100% voting, you got 30 point or favorite point. So basically, 30 over 100 is the ratio, basically ratio of score versus total people voted. And then basically, she has a score of 90. So basically you do a ratio, and X became unknown. And we know that we scale from 30 to 90 by multiply 3, then you multiply 3 to get 300. Let's see this problem. Yeah. This problem basically is about prime factorization and index counting. And so basically the first step is that we had to complete factorize 4,000. After we complete factorize 4,000, basically we actually got 2 to the 5th multiply 5 to the 3rd. Then it claims that n can be either positive or negative. So basically we know that n equal to 0, then it's just 1. 2/5 to the nth is 1. So basically, it's still, the result still integer. So that's the first case. Then the second case is n positive. N positive is just this way. And the denominator is 5. Denominator is 5. If it go too high, you're going to have 3 completely canceled out and have extra on the denominator. That will make it fraction. So basically the highest we can go for n is 1, 2, 3. So that's positive. Then n negative, basically we actually have to reverse the multiplier into this format, and we let m equal to negative n. Then basically m can go from 1 to 5, because if 2 is on the denominator, m can go as high as 5 to still have the whole expression as integer. So basically when n is positive, it takes this form. When m is negative, the multiplier becomes this, and I'm using the m as the the absolute value of the positive opposite of the negative index. I can calculate this case and find out you have 5 cases working. So the final count is 9. And then for this problem, is actually, it's a Diophantine problem, which The funding problem basically is you have multiple variables and trying to figure out the integer solution in a certain range. So basically, I am defining the dime, nickel, and a quarter number of those only by a thing, like only by two variable. So one is the n, it represent number of the nickel, dime is n plus 3, and the quarter is n plus x. X is how many more. This is what it wants. And then after I make the expression, I can simplify this whole thing. These are very straightforward. It's just expanded and simplified. After you simplify it, what you get is actually this equation. And this equation, obviously, we have certain restriction. And the restriction we are having is that the 25, we see the 25 basically, has to be a multiply a even number to get to 0. So basically, given the option we have, we can only find the even number, and the 0, 4, and 2 are even, and 1 and 3 is out. Because if we take x to be odd, we simply cannot get 0 on the final digit. Then we kind of just place 0 in, and 0 obviously do not work. If it's 0, basically it's going to be you cannot complete divide 290 by 40. Then you also, then the second time just try 2. Try 2 is actually already working. So if it's already working, then it works. Then if it do not work, so just try 4. So I think this type of problem is not too difficult. One of the thing is that it's a Diophantine problem. Also, it has the limited answer here. You can test your result into the formula you build yourself. And so this problem is trying to calculate the area of the trapezoid D, B, C, E. So basically, we are really trying to calculate the ratio of those each of the 7 similar. So the bigger triangle has 40, and then the little triangle has just area of 1. Then basically, in this type of problem, you actually can, for me, I actually just make a false assumption that the length of the side basically, what I did is that just assume the ratio of the side, then you do some manipulations and you will be able to get it. So let's go to the next one. Yeah, this type of the problem for me is still trying to do the algebraic manipulation, and radical problem. You usually, let me just copy this problem and try to do it again. So basically, radical problem possibly worth some effort to talking about. So usually it's very hard to handle two radicals. It's much easier to handle one radical. So the way to handle one radical is that you put 49 minus x squared and equal to 3 plus and 25 minus x squared. So you actually, this is a standard operation in radical handling. So when we trying to move to the other side and try to completely square it, we actually get rid of the radical on at least one side. Then this is going to be 9 plus 6 square root of 25 minus x square and plus 25 minus x square. So basically here we can cancel this out, and then we will, this is actually 34. And 34, this minus it, going to be 15. 15 going to be equal to 6 square root of 25 minus x square. So here we can, this is just 3 multiply 5 and equal to multiply 3. So we 25 minus x square, we can cancel this out. So here, then we can complete square one time more again. So that will help us to really figure out. So this is going to be like 25 equal to 4. And this is 25 minus x squared. So 25 is equal to 100 minus 4x squared. So 4x squared will be equal to like 75. So x squared equal to 75 over 4 equal to like 3 multiply 25 over 4. Then we complete squared. Right now we take the square root. So this step we are taking the square root. Then we got like square root of 3 and like 2/5. So basically, we will be able to do it this way. And also, basically, here we actually already reached this because we are not really trying to calculate x. We only need to calculate x squared. So basically, after reaching this step, we actually already get it. So we can already begin to plug in, and then 75 over 4. So 49 minus 75 over 4 square root plus, this is 25 minus 75 over 4. So here basically it's just going to be 49 multiplied 4 equal 196. And this one is at 4 over 100 over 4. So this part, basically, it's going to be like 25 over 4. And this part, if we minus it, going to be like 121 over 4. So both you can actually square root out on it. This is 11 over 2 plus 5 over 2 equal to 16 over 2 equal to 8. So this type of the problem, just if you just apply the standard method, it's doable. And this problem, yeah, this problem basically, the 7 dice, it's asking the probability, and it's a 7 dice, and every dice could be repeated. So basically, it's on the bottom. It's very easy. It's just 6 to the 7th. What's the probability? Sum of the number on the top faces is 10. So the sum of the faces on all the 7 dices is at least 1. At least 1. And then the problem is how to distribute the 3 extra extra 3 points so that they will add up to 10. And imagine that the first dice get an extra dice. You actually can get 4. Then the rest is 1, 2, 3, 4, 5, 6. So basically, the first dice could get 4, and the second dice also could get 4. So basically, it's just a matter of how you arrange those like 7, arrange the 3 point in the 7th spot. So the 7th spot is, I label it 1, 2, 3, 4, 5, 6, 7. And I'm not labeling the 7 spot by number by itself. I actually labeling the separator. So I have separator. I have 1, 2, 3, 4, 5, 6. So these are 6 separator to separate the extra 3 point. The 3 point actually not using the number because using the number very difficult to represent. So I'm just using the pure circles. So basically I can use those 3 point I can allocate here, here, or here. So basically if I allocate this way, basically, the first dice is 2, the second dice is 1, the third dice is 3, and 1, 1, 1, 1. So basically, it's arranged this way. So this representation, this actually is a very famous trick called like, stick and stone. I think we already taught that in our class. So this is a stick and a stone trick. The stick and stone trick, using the stick and stone trick, what you will see is that, there are three stones with 6 stick to play. And basically, so add them together, it's 9. So it's 9 pick 3. So 9 pick 3. 9 pick 3 is actually the the value we are going to go after. 9 pick 3, you actually is able to calculate that out very easily. The number is 84 because 9 multiply 8 multiply 7 and 3 multiply 2 multiply 1. So this is going to be 3, this is going to be 4, and that's going to be 84. So basically it's going to be like, 84 over 7 or 6 to the 7th. And if you use you can build cases and build cases basically, it's just a lot of cases. And you had to build 3 cases. If you use stick and stone, you just build 1 case and solve everything. So that's the advantage of using this method. And so this problem, I actually did all the problem without checking the answers and try to check it. And this problem is just a lot of drawing, basically. Yeah. So we actually had to build a lot of case. And by building each case, you will be drawing out those kind of the lines. That because there are how many lines we have, the blue line. So that's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 lines, and how complex is. So basically, those lines actually represent, the data happening in different partition of the plane, the Cartesian plane for this function. And then you have this one as a line. So basically, this is a line. How many lines is going to cross those blue lines? The blue line represents the, and so how to draw out the complete blue lines? Basically, you just build a case, and if x is greater than 0 and y is greater than 0 and x is greater than y. So x is greater than 0 and y is greater than 0. So it's in the first quadrant. And x is greater than 0. Basically, it is in the, you split the first quadrant in the 2 halves. it's in this position. For example, this is actually 2, 1. You can pick a number to represent that area. So in this area, if all this is true, then basically the second, this one represent x minus 1 equal to 1. Then you transform this into the like y equal to x minus 1. So x minus 1. So basically, when you build a statement like this, you build one branch because there are 3 absolute value. Each absolute value will create one set of conditions. So you have 3 independent condition. Each condition create like 2 opposite of case. So 2 to the third is actually equal to 8. So that's why you have 8 branch. So I'm just showing you how to draw one branch. And this branch basically is in the first quadrant and satisfies this condition. And so in the end, those, whether or not x bigger than 0 or y bigger than 0 and the comparative value between x, y, create 8 conditions. And actually in 8, so if you split this Cartesian plane into 8 equal sized shape, then in each area, so in each area, it actually has 1, 1, 2, 3, 4, 5, 6, 7, 8. In each area it's a straight line within that scope. Then this line obviously is universal. It's not limited to any area, but it only creates 3 intersection. And yeah, because in this area, and this line will get into this area, but they will never intersect in this area because it's going down very fast. It's staying relatively flat over there. And then this intersection is just intersect at the tip. So if you really do the drawing and really do the casework, it's like 3. I think let's call it off for today because I don't think we really will be able to talk too much on the remaining. I think one of the ways that let me show you where you really want to review and I think after the test, if you guys are interested, we're going to just continue on learning at like a slower pace. Then we'll be more thorough in talking into each topic and do more detailed exercise and also do more history test work. And let me show you where you can find the answer. And so basically, and the sample test is actually 2018 AMC10. So basically, if you go here, you actually is able to find the solution. It has the solution, and some of the problem actually even have the video solution. So basically, you are able to dig more into it. And a lot of problems have multiple solutions. So basically, some some of the problem I think is relatively easy, so I just use, if I can solve it very comfortably, I will just use my method. Otherwise, I will look into several different methods. And for example, this is a blocker problem, and actually, um, there are several different ways. For example, the solution 3 is absolutely unnecessary, and so solution 3 is actually, so if you reading those solutions, if the solution makes not too much sense to you, just ignore it, because some of the, for example, solution 3 on this problem, on the problem 4, actually is using PIE. PIE is principle of inclusion and exclusion. It's a very advanced technique taught in the like intermediate, like probability and statistics. So if you really read into it, I think you will confuse yourself more in doing this problem. So basically, uh, I think, you know, if we just keep on going, it's just going to take another like at least 1.5 hours. So I think we already at the time, and so, and also, you know, your test is so close. I think the purpose of this class, because we cram so much things into very few classes, we are not really totally prepared. And it's just gave you a showcase of what you at least need to learn. Actually, there are much more to learn. And so if you are interested, we can continue a slower pace. So, you know, each week we'll just study 1 hour, and then it's going to be a long-term preparation, because uh, you don't expect to really get top score in just one trial. And all of you are very young and have plenty of chance to try more. So basically, if you just keep building up, when you reach the appropriate age and grade, you should be able to get a decent score and get much better grades than other people in this type of the competition. And it just take preparation and study and the practice. In the end, you will, you know, privately, you have to spend a lot more time. Obviously, you have to go through all the historical problem, and also just push yourself a little bit more by, you know, time yourself doing this type of test multiple times, and pace yourself in the right time usage. And otherwise, you could be like, you know, give you 3 hours, you may be able to finish every problem, but basically it only give you 75 minutes, and you actually have to, in the real contest, you actually have to pick and choose, because it's very rare for people to finish all those problems. And for this test, actually, you know, it take me about like 4 hours to finish everything. Actually, I did everything right. So, but if I really have to give me a score, possibly I will get like maybe um, maybe maybe 80% or less. So it's not going to be very good. But for me, it's more kind of studying and trying to find the best method, and trying to, I'm not so, but if you really want to go for a good score, a lot more practice is extremely important. So kind of only 2 or 3 days into this class, and hope you good luck on the test and have a nice one. And I'm going to send you the link to the, you know, the test solution. And so basically, if you really have interesting to go through every possible solution that publicized, you can actually do it yourself. Okay.